Thank you so much, everybody joining today's NC-CAV seminar. We are delighted to have Dr. Yaobin Chen as a speaker today, and the title of the talk is Design of Standard Crash Scenarios and Testing for Vehicle AEB Systems. A little bit about Dr. Chen. He's a Chancellor's Professor of Electrical and Computer Engineering and Director of the Transportation and Autonomous Systems Institute, TASI, in Purdue School of Engineering and Technology, IUPUI, Indianapolis, where he joined in 1990. He received his bachelor degree from Nanjing Institute of Technology, China in 1982, master and PhD degrees from Rensselaer Polytechnic Institute, Troy, New York in 1986 and 1988, respectively, all in electrical engineering. Dr. Chen's areas of expertise include autonomous and connected vehicles, intelligent transportation and safety systems, EV and HEV, and advanced control and robotics. He has published 180 technical papers in referred journals and conference proceedings. He's a co-investor of 8 U.S. patents. He was a recipient of the National Science Foundation Research Initiation Award in 1991. At this stage, I also would like to thank the sponsors of the project: North Carolina Department of Transportation, Downtown Greensboro, Verizon, and RTI. With that, I would like to pass the take it to Dr. Chen. Thank you so much.
Thank you very much for a nice introduction, and it's my great pleasure to meet with all of you virtually, especially my old friend. We actually work on a project at the UTC Center, led by the Ohio State University for 3, 4, 5 year period, I remember. And also some other, like Ali, we talked virtually, via Zoom. And I really appreciate the opportunity to share with all of you some of our research programs here. Should I just share? Can you get out of sharing?
I try to stop sharing so that you can.
Yeah.
Okay. Now
okay, great. So let me do my job here and share my screen first. Okay. All right. So let's see. I need to somehow hide something. By the way, we're a Zoom user. I'm not very used to WebEx. I attend a meeting with WebEx. So maybe I just minimize this. Okay. All right. Okay. Can you see the slides?
Perfect.
Okay, great. Thank you again. So the title of my talk is a little bit slightly different than your seminar flyer announcement there. I changed it a little bit. So the title is the Development of Pedestrian and Bicyclist Crash Scenarios and Vehicle AEB System Evaluation and Testing Methodology. So as suggested by this title, the ultimate goal of this research project is to develop a vehicle to pedestrian and bicyclist crash scenarios, and also we need to develop the evaluation methodology and also testing procedures for automated emergency braking system, which is was designed and used for mitigating vehicle crash or collision with a pedestrian and a bicyclist. So with this title, we know it takes a lot to do this, and in order to have a right testing results or evaluation method or performance metrics, we need to have right set of crash scenarios. Those scenarios are not just imagined by our brain, by our head. We have to based on facts, based on data. So that's why in this talk, if you look at the outline of this talk, Before my technical presentation, I really want to share with you a little bit about our research institute called TASI, Transportation and Autonomous Systems Institute, which was founded many years ago. And I'd like to give 5 minutes a quick, overview. And then I'll follow the outline here to give you a little bit of motivation and background of the project, and then the approaches, plans, the process we follow through until the end. After we develop such a system, vehicle performance testing and evaluation, then we also did a benefit analysis for such kind of technology deployment. If we have this on our production vehicles, how many lives we can save, how much money we can save. So that's we call the benefit analysis. So with that, I want to start the presentation. And again, I really want to thank some sponsors for the project, and also my faculty and the staff and the students. So first of all, this project overall, most of the part of work I presented here was sponsored by Toyota North America through its Collaborative Safety Research Center, we call the CSRC. If you have not heard the program, that program was launched in 2011. Actually, a couple of days ago, we attended their 10th year celebration showcase workshop. And our research center was one of the first 4, 5, or 6 universities that received funding. So for our project, it was a multi-year and multi-million dollars. A lot of people were involved. So I really want to acknowledge my faculty collaborators, our research staff, and the students from our campus, from our partnering university and campus, including Indiana University, Bloomington, and The Ohio State University for their research contributions to the project. And again, this project is not my own. I serve as a PI, but we have, from beginning to the end, we have probably 50 to 80 faculty, staff, and students involved, including many undergraduate students who help us in a large-scale naturalistic driving data collection activity. So that's why it took so many people to do it. So within a short time period, I'd like to present our major results, and hopefully you understand, what we did, what we accomplished, and what kind of significance or impact on our transportation vehicle safety, on road safety. So before that, I want to quickly just talk about a very brief introduction to TASI. And I think my friend there, we worked together at a UTC center, probably he knew a little bit more before this presentation. As I mentioned, TASI was founded in 2006. I served as a founding director from beginning until now. And our original goal and mission is really to conduct cutting edge, research in connected and autonomous vehicles and intelligent transportation systems through collaboration and partnership with academic institutions, industry, government, and other research organizations. So we see there are 3 big parts of partnership here: academic, research centers that involve faculty, students from our university, from other partnering universities, and the industry, those automotive suppliers, OEM, other transportation-related business companies, and the government, federal and state, DOT, and some other research organizations. So TASI was founded on day 1 with multidisciplinary faculty researchers on our campus, and also we have faculty from Purdue West Lafayette, Purdue University West Lafayette, and IU Bloomington. So 3 campuses, basically, we came together and established a center, and with a really multidisciplinary research skills and expertise, including those typical areas which are important to connected and autonomous vehicle research and ITS research, like sensing and perception, different sensing devices like radar, LiDAR, cameras, and so on and so forth, system simulation, control, wireless communication, and cybersecurity, data analytics, human factor engineering, and user experience design, and AI, AI and deep learning, which are important tools for us. And we also work with some kind of psychologists with focus on behavior and cognitive science to look at the vehicle driver and pedestrian bicyclist interaction behaviors and in counting modeling. And we also work with business and public environmental affairs faculty in public policy and the regulation area. So it's really truly a multidisciplinary collective teamwork to make this center a success, a model on our campus. So these are key research partners, including universities, industry, and government agencies. So I don't want to go through one by one. You can see we have major OEMs and suppliers, Delphi, Aptiv, GM, Ford, Toyota. So especially our work with Aptiv or Delphi and Toyota and Ford, 3 companies have really lasted more than a decade continuously. So that's very significant support for our research activities. And on these slides, you can see kind of glance at our research labs capabilities, facilities, and some research projects, like some pictures you can see. So under TASI as a center, actually within our school and with faculty members from other departments and other schools, we have a physical space like major research laboratories of about 7,000 square footage. We have lab that can handle cars, vehicles. We can do experiments inside, and we can make things in our lab. We have a very good we call it workshop space with a lot of tools, mechanical, electrical, and other tools to make things happen. And we have a driving simulator, like based on 1/3 car cabin with I think a kind of projection screen, typical, I call it low cost driving simulator, not including the full motion, 6-degree of freedom stool platform. But this one can help us in many research projects when we deal with the human-machine interface and the human factors aspects for driving. And you can see some of the pictures, that highlight our current activity, like e-scooters, and also we have vehicle instrumented with LiDAR with 6 cameras around 360 degrees. We also have a leased test track. We call it leased. We leased a test track from a company, and we have done a number of vehicle testing kind of experiments using that test track for the last since 2012, I think. So you can see something here. They look very funny. Those are you call dummy or mannequins. They were specifically designed for crash kind of a test. So it's I call it crashable mannequins. After crash, even hard hit, we can recover, reassemble very quickly within probably most time 2 to 3 minutes. Sometimes it took 5 minutes to put together. We have pedestrians, we have also bicyclists, and we have also done other things that we call the roadside objects surrogate, like a curb, a concrete divider and a metal guardrail and other things. So this is just a summary of some current research projects. I don't want to go through. One of them I highlight here is we have been working on a predictive model for e-scooter and vehicle interaction and encountering. So you'll see some picture here. And again, it's kind of data-driven approach. We have collected data in Indianapolis area for the last 2 years. This summer, actually, we're going to different places in East Coast to West Coast and also South part of the US to do, for every place, we plan 2 weeks data collection to look at if there are some differences between different regions. So that's an ongoing activity. And we have worked with the Indiana Department of Transportation on traffic ITS related projects, including speed management strategies and video data analytics using installed cameras on Indiana highways to kind of detect we call the automatic detection of traffic incidents and vehicle classification and all other data we like to derive from there. And we have been also working on a Ford-sponsored project to look at the future autonomous vehicles in terms of reconfigurable seating. If you look at the future, passengers and we don't call drivers, no drivers on autonomous vehicles. People can sit in different configurations. They can talk, they can chat, they can play cards, they can, probably eat. And what if there's a crash? How we protect those occupants? So that's what we call the real-time in-cabin occupant sensing. So that's also ongoing project. So with that, I like to switch quickly, come back to the main focus of today's talk, which is development of pedestrian bicyclist crash scenarios and a vehicle AEB system evaluation and testing methodology. Before I do that, when I say, okay, that's the goal, right? So how we can achieve that goal? And we really need to think hard. How can we come up with vehicle to pedestrian and bicyclist crash scenarios, which can be used for standard testing and the evaluation of system performance? You cannot, ask anybody, any OEM, to test their system, test track for 1,000 different scenarios, right? You have to find something typical, something representative, something can tell you as a core, something can tell you how system work, if system work, to what kind of level the system will perform. So that's like a star rating type of things regulated by NHTSA, by government agency. So we need those, we need the data, we need the facts in order to have those, in order to develop something implementable, something workable, something that can be accepted by the industry and by the government agencies, and also by the public, because for any OEM, they can develop automatic emergency braking for pedestrian crash, for example. And as consumers, we really don't know how that system work, how to perform. You cannot put a real life person in front to give a try, right? I heard somebody tried that and then crashed a person. So as a salesperson, they want to demonstrate, they have no way. Anyway, so that's the motivation there, is to develop such technology, I call it overall technology, for system testing and performance evaluation, like performance metrics. So we have common standards. To achieve that goal, we need data. We have crash data, but usually crash data base, the data really don't provide the full picture. It's after the fact, from police report, for example. So based on that, we say, okay, we need to do a little bit more, work here, and So that's what drove the research project. It's like a step-by-step, a very systematic way and a data-driven process. So before that, I have a couple slides. I just want to point out, why we're working on this. What's the driver there behind? So for those in the audience, I think most of you are expert in transportation systems, including safety issue here. So from U.S. Department of Transportation, from annual NHTSA's vehicle crash report, I found that the latest information up to 2020. So we still see, if you look at the historical data here on this chart, from 75 to 2020, in terms of total fatalities due to the vehicle crash, they have not changed too much. They decreased a little bit, right? You can see. But overall, if you look at the magnitude, look at the order of magnitude, look at the range, they pretty much stay around for the last 10 or some years, like 32 to 40,000 lives, fatalities. Most recently in 2020, the number has really increased. Okay, so you look at the number here in 2020, the car crash fatalities, the number is 38,680. So that's really high. That's the highest if you look at the last 10 years. And when we look at the data from the US DOT website, for the first 9 months in 2021, the final data probably has not come out. Probably it's out, it will be out anytime. Just for the first 9 months, we got more than 31,000 deaths due to vehicle crash in 2021. So people expect the total number of fatalities probably will be more than the year before, which is 2020. And among those fatalities, you can see I call the vulnerable road users, like a pedestrian and a bicyclist. The numbers are also increasing. Okay, I don't need to go through a lot of detail. All of those crashes, accidents, or something also imply the cost associated with it. If you look at the CDC study or reports, you can figure out that they're in kind of the number I have here is from several years ago. It's about $99 billion. So that average to each US driver is like $500 for each driver, just like us in 1 year. So that's the cost. It's a really very serious problem, especially for vulnerable road users. We are adding one more, right? A big one. You probably remember I think it's about 2018. Suddenly, after summer, when students and the faculty returned to the campus, we saw a lot of e-scooters around downtown Indianapolis and also around our campus. And according to data, probably more than 100 US cities, in downtown, town center, they got a number of e-scooters starting from that year. I think it's a widespread. So e-scooters are, even from our early, study, even more riskier than bikes and the pedestrians, in a sense, the speed and the way a lot of local ordinance require e-scooter riders ride their e-scooter in driveway, on the road to share with cars. So they're not allowed to ride on like a walkway, pedestrian walkway. It is kind of scary, and you see for our current study, we have seen a lot of things already, but this talk is, we just focus on pedestrian and the bicyclist. We all know the reason. I don't want to emphasize more. Distraction, driver's distraction is the primary factor for this. And according to data, we know that driver inattention. So that's the major cause of vehicle crashes, and also daylight time. It's a bright daylight time and a good environment. It's not like you have bad weather, snowing and raining. You see that. So that's the point. So we know how, historically for many years we know the problem. We just need to address. We just need to come up with a good solution to ultimately we call the zero fatality, zero something called zero, right? We don't want any deaths, but we are far away from there. And in this diagram, it shows kind of 5 different stages or states the driver usually goes through. And especially if you look at this slides, the middle one, then the last 3, which are very critical, and we call the mitigation zone. If we don't have automation, we don't have those ADAS system, if you rely on driver, data shows driver distraction, driver whatever reason, is a main cause of most vehicle crashes. So it's very critical to address these last 3 states. And you probably all know, some of you probably are driving relatively newer cars from different OEMs, and they come with more or less some kind of ADAS system, advanced driver assistance systems, and they come with some, we call the active safety technologies that can help drivers to drive safely. So that's the thing. So in this research work, we're trying to address something in the last 2 stages, the 4th state, meaning if the driver is driving, if we have pre-crash warning and the driver, didn't take action, and it would be late if the driver, take action. At that moment, our advanced active safety technology, that automatic controller will take over. So in this case, would it be AEB system, automatic emergency braking system. So that system will be triggered and will really brake hard. I can tell you my personal experience, when we started to work on this kind of technology in 2008, we had a group of people to meet and visit the U.S. Department of Transportation, NISA people, with their executives there and their researchers, and we demonstrated a research version of pedestrian automatic emergency braking technology on top of Nationals baseball, the parking garage, and I tried to jump in the car. It's a Volvo XC60. I drove, and our engineer told me, Dr. Chen, you just drive, don't hit the brake. There was a pedestrian mannequin in front of a car, so when the car get close, I suddenly just push the brake. Because that's an instinct, right? As a driver, I saw something there, I have to brake. So then they said, no, you don't do anything. We have an automatic braking system there. So then the second time I tried, I feel scared, because I watched the car approaching that so-called pedestrian dummy or mannequin standing there, and my car just almost hit that one. So fortunately, the system worked at that time. So the car fully stopped. So that was a research vehicle. We worked with Delphi, Aptiv, and Volvo back then. Anyway, so there are a lot of things out there, and the focus for us is to develop something for automatic emergency braking system. Different vendors sometimes use different terminologies, but in academic research, I think most of us use the AEB system to represent such kind of technology. And in this slide, you can see a lot of things like adaptive cruise control. And then I also showed something from GM, Cadillac Super Cruise. That's kind of level 2, between level 2, level 3 autonomy. And we work on a project we call it semi-autonomous driving. program from 2009 to 2011, 2.5 years, 3-year period, funded by the Federal Highway Administration, cost-shared by GM and Delphi. So we, as an academic institution, as a partner, we work on the project. So we did a lot of work, on the driving simulator to see how this highway autonomous driving works. Meaning, if you're on highway, the traffic is better than local, like a city, and with adaptive cruise control and a lane centering control, then with a lot of pre-collision warning and also driver state monitoring, driving state monitoring sensing and alert system. So, it worked. So that's the technology we have today in the market. Okay, let's just move quickly to what we can do, what we should do in this case. And we have several basic questions we need to kind of answer. We said we want to develop standard crash scenarios. And the first question is, what kind of crashes are the most important to mitigate? Okay, because when you do standard testing, you cannot come with 100, 200. It's even there's so many different scenarios when vehicle crash, collide, into pedestrian or bicyclist. So then we need to understand what kind of crashes are most important. Okay, if we define what kind of crashes, then we need to answer. We need to figure out how to. What to test, how to test, and how will the system work, right? So that's we call the star rating and performance metrics development and evaluation methodology and so on and so forth. So to do that, we said, okay, data are very important. We know we can access national crash database. There are a lot of data there. Most data there were probably produced by police reports, and they can only, I think they can only speculate or just, I don't know, or what we can say. It's after fact, after crash, you go there, you try to reconstruct the scene, right? So that's kind of data we can access. And we don't have much in terms of exactly couple of seconds before crash, the real scenario. So therefore, we say, okay, let's do this. Let's collect data. So working with Toyota in our industry, our partner, we designed we call the naturalistic driving experiment. So this one is a really large scale. At that time, we figured this is the only one after next to Virginia Tech VTTI 100 car study. Eventually, when we publish a paper based on our data, we call TASI 110 car study, because we eventually collected data for 12 months period, the whole year, for more than 110 drivers, subjects, of like 18 years old to 68 years old. They drive on their daily. They drove their own cars, instrumented by us, and for 12 months period in Greater Indianapolis primarily. But if they take a short trip to Chicago, to nearby cities, we also recorded all the data. So we do have data, from Chicago, from Ohio, from Columbus, Ohio, from Cincinnati, from St. Louis, from other neighboring major cities as a result of this data collection activity. And by the end, we got about 100 terabyte naturalistic driving data with primarily high-def video data and also other vehicle data. We have a G sensor, we have GPS, we have other related data. So with this kind of high-def video data, we're able to really look very clearly, look at the pedestrian and the vehicle interaction behavior, look at the cyclist and the vehicle encountering behavior, and we can develop some models validated by those data. And even today, the data we collected, our video data, they contain everything and all kinds of things. So this set of data, big set of data, very useful even for other purposes. So in that project, our focus was on pedestrian and bicyclist behavior. So we use that to come up with models, and some parameters that were interesting. For example, we really want to see what kind of speed people walk when they cross the street, for example. So they are in such a range, we want to find a range. And then we also want to analyze their gait movement, under different situations. And then we use a data mining kind of tool to analyze some more subtle behaviors for the purpose of design. Okay, I assume you are still with me. Can you hear me clearly?
Yes, of course.
You do.
Okay, sorry, this is a virtual world, I don't see you, I don't have feedback. That's wonderful. So let me just show you some kind of video clips very quickly, and you can see what kind of, can you see the video, movements smoothly?
Yes, but there is no sound.
This one, we don't have sound. Yeah, this is just the video. By the end, if I have time, I want to show you a Discovery TV program. So they made a program from our research project. So I will show you a couple minutes. Actually, there are 6 minutes in that program, but I will show you that one with sound. So you can see the bicyclist, you can see, pedestrians. You see this is like a shopping somewhere, and we also have a night driving data. We see people walk, not sidewalk, they walk actually on the road. We see pedestrian crossing. We see all kind of things, right? People pushing shopping cart and bike, on the road, and sometimes the sidewalk, and the kids are going to school, and all kind of things. So sometimes you see some crazy things, but most time you see those how people live, how people drive, how people walk. It's kind of interesting. So when you see that. Anyway, so this is the kind of data we collected, and for 12 months for each driver. Initially we recruited 125 to 130 for one reason or another. Some of them were disqualified. And I think by the end, we have 116 subjects or drivers who completed the entire 12 months. So we simply call our data set, tested 110 car data set. So we saw
just one question.
Yes, go ahead.
Any of them ended up in a real crash or no?
Okay, very good question. I tell you, even I put there is like 1.44 million miles, right? A lot of miles, lot of hours. We only identified for pedestrian crash, single digit, very close to crash. Literally is a crash, but no fatalities, no deaths, no, very serious injury. Okay, number one. Number two, for bike, we see something very close, almost like a hit, but not a very serious accident, injury. So first of all, no deaths, that's good. But according to NISA's data, if you only have this kind of things, statistically, you probably don't expect any deaths here. So we saw some collisions, some crashes, definitely crash, but not that serious to the extent of fatalities.
I see.
Okay. All right. So then we also, for this data analysis, it's really a very large scale, and we hired many senior and first year graduate students, we call hourly students, to do a lot of labor work. We have both manual and automatic kind of processing, pre-processing tools we developed for this purpose. And by the end, we developed a pedestrian detection algorithm, bicyclist detection algorithm, because by people watching video so much, so many, kind of big data there, it's very time consuming. And we end up with those kind of automatic tools to do in-depth analysis, especially we call the behavior analysis and the modeling. So we do that for those who are in image processing, in pattern recognition areas. Especially today, we talk about AI and the deep learning. For behavioral modeling, prediction modeling, we use this kind of tool a lot. So in this project, we develop some tools, and with assistance of manual work, eventually we figure out enough, kind of we call the near crash, and also. That's the only thing we're interested in terms of crash scenario development. Any other things, they don't really help you. So we also estimated the time. We call the TTC. It's called the time to collision as some kind of metrics to do those things. So we have published extensively from this project. So if you just search my name or my colleague's name, you can see all the papers. So I'm not going through a detailed algorithm per se. So we have pedestrian cluster measure approach. This is a block diagram that shows the process. And we have done some categorization based multi-stage pedestrian detection. So this is the kind of block diagram or flow chart which shows the process. Similarly, for bicyclist detection behavior analysis, we develop algorithm. We develop the tracking algorithm for bicyclists, and these are some images, some video, some pictures that demonstrate the process. Okay, let's see. Those things are done. Okay, now we still need to figure out crash scenarios. So in general, for crash scenarios, we have a number of, I call the parameters we need to consider. First of all, for pedestrian and bicyclist, we need to look at the behavior parameters. Something describe the behaviors. For example, for pedestrian, we have crossing. Pedestrian cross an intersection, a road, straight, standing, jogging, walking. We're interested in those behaviors, right? If they're walking, if they're jogging, if they are just standing still. So that's a so-called pedestrian behavior. And then vehicle. We need to look at the vehicle motions. If we're traveling straight or it's a turning, we're interested in vehicle speed. So that's important, in any kind of crash scenarios development. Then we're interested in environment. What kind of environment? Where? Where it is, right? It's an intersection. It's just a middle road block. We are interested in lighting condition. It's dawn. It's daylight. It's evening. Morning, and want to know the weather condition, and then want to see if there are obstructions there, right? And for pedestrian, for this object, pedestrian. For pedestrian, we're interested in their age, gender, and what kind of clothes they usually wear. What kind of clothes most people wear. Because when you develop a standard crash scenarios, you got to have mannequins, pedestrian mannequins or dummies. So what kind of color of clothes we put there? So that there are a lot of things you look at that. So this slide just shows like a flow chart type of things. Like state diagram or flow chart, which illustrate the idea, the concept I just mentioned, and then eventually come to some results, some numbers we can use. So for that purpose, we decided to look at 3 different standard pedestrian. One is a kid, child. For child, we feel, 6 years old, average child. So that's the one we can choose. Then for adult, we don't distinguish between genders. Female, male, we just look at the average adult. So initially, we kind of categorize adult into 2 classes, 2 kind of them. One is a normal one, we call it fit adult. Second one, obese. Certain BMI above a threshold, we call it obese. By the end, I can tell you, when we share with our industry partners, share with other professionals, they felt there's no need to have a bees adult as a part of standard testing scenario. So we did those, and we also made it happen, okay? So after that, we have behaviors, we have scenarios, and we have definition of what kind of pedestrian standard pedestrian we are interested in. We said, okay, one is adult, male, female, average, in terms of body build, in terms of geometric, size and dimension, all kind of things, weight. And for child, we pick 6 years old, as a standard. So we have an adult, we have a child, and as I mentioned, the project was sponsored by Toyota, and they named them. Okay, we have Steve Jr. Okay, so they also took the dance, to Consumer Electronics Show 2015, and they gave a big presentation on their new technology for safety, and one of them is this sense, we developed. So this is was really uniquely designed, specifically designed to reflect the human body characteristics and properties perceived by sensors. We look at 3 types of sensors. We look at radar, we look at LiDAR, we look at a camera. And then for these pedestrians, they walk, we generate a walk trajectory, and they look like a real human. And we invented a special clothes, fabric. It's a metal, we have metal layer. It's like a secret recipe, with different ingredients. And we got a patent, US patent, international patent. We also played an important role for SAE standards for pedestrian mannequin design. So similarly, oh yeah, by the way, one of the things I didn't mention is we did a Readout cross-section modeling, and we have a blue and a red here. They represent pedestrian mannequin and a real pedestrian person, real biological person. And the spectrum here, if you look at them, they match very well. So that means our design, our pedestrians can really mimic a real person. Similarly, we went through a very similar process for Bicyclist. And we also helped the SAE develop the standard for Bicyclist design. And this Bicyclist, if you look at the radar cross-section response, you can see how they fit, match each other. Real person, real bicycle, and with the rider, plus mannequins, and a real bike, and our mannequin bike. So they really match very well. So this is one of the early generation we have, in the picture. Okay, we have tools. We have mannequins, dummies. And now we can kind of put based on data analysis, based on the crash database analysis, based on data we collected in our TASI 110 car study, we eventually figured out, scenarios, crash scenarios. And this is one of the example from crash database. So that's like a police report. So they tell you this crash happened, when the vehicle moved from this vehicle moved from a direction. I think this is north-south direction, and then the pedestrian is somewhere here. And so basically we have those kind of data. Then for cyclists, for pedestrian, we have this different scenarios. If you look at the vehicle motion direction, look at the pedestrian or bicyclist, there are a lot of detail here. Okay, so I'm not going to go through a lot of detail here. So with the scenarios, with mannequins, with everything, the next thing is our testing protocols and testing procedure and hardware, software. So on this slide, you can see our overall ADAS testing system setup. So this is setup, with the data, with the control system, with everything laid out on a test track. That's how we set it up. And then we use wireless communication to control different sensors and different mechanism. And for this testing, we have a gantry type of motion control system to move the pedestrian, because it's hard to make the pedestrian mannequin to walk like a human, real walk. That's like a robot. You see how robot walk. It's not like a human in general. And also, lessons should be designed in a little bit easily maintained and also crashable. For any walking robot, if it got hit by cars, I bet you cannot, recover that dance in a few minutes. So that's some other consideration there. So we recommended 5 test scenarios and 10 test scenarios. Which 5 should be, which 10 should be. So in this table, we have that. And we have a light condition, we have some other conditions. So all of those factors, combinations, give you so-called the test scenarios. So we did testing like this, show a picture, nighttime, and then we have different scenarios. And I'm going to show you the video very quickly so you have a better sense. Similarly, for Bicyclist, we also develop the test system and with hardware, software control and everything. And for bike, by the way, at that time when we did the research, we cannot find a vehicle which can really perform under different scenarios. So we can only test a couple scenarios. One of them is like this, okay? The bike cyclist just ride along the same direction as the vehicle is behind. And then the other one is cross. So for cross, none of the system worked. At that time, the only system working in this scenario was a new Volvo XC90. So this is a vehicle, we tested. So in terms of test scenarios, we only tested very few for Bicyclist. Okay, any questions? It looks like I'm running out of time, but I only have a couple more slides to show you, I think. Okay, so let me quickly show you something here. I have so you can see, so this car comes with AEB. So it automatically stops there. It's not by driver braking. So it depends on speed. Just to let you know, if the vehicle moves at higher speed than 35 miles per hour, usually it doesn't work. Okay, so for the future autonomous vehicles, I don't know what to do with that. But again, this kind of system was not designed to function in interstates in highway speed, because you don't expect their pedestrians suddenly pop out from roadside, right, highway. So that's the thing. Let me just show you one more with the Bicyclist. So for Bicyclist, you see, we cannot use that kind of gantry motion system. We design a motion, like a mobile robot, we call it carrier, to carry this. So we also have a nighttime scenario. That's what we do. We still use a gantry type of structure, and we'll hang in there and then move it and to simulate our walking. And we can control the speed for this, definitely. Okay, so with all of that, the last piece is a benefit analysis. So I don't want to talk about this. We have some kind of mathematical model to estimate, to do benefit analysis, see how much money we can save if we have this fully deployed, how many lives we can save. So this is just a preliminary analysis results. So we say if every car comes with this system, we can kind of reduce the crashes by 20%. We can save about 1,000, people's life per year, and we can save a lot of money, $10 billion in social costs per year. So that's just based on like 5-8 years ago data, maybe 8 years ago. Okay, so with that, with that, I just wonder if, let's see, we only have 2 minutes. We started late, right? So we can extend for 3, 4, 5 minutes.
If your time allows, we certainly would love to have a conversation after that. But thank you so much. That was really impressive time. Thank you. Thank you so much. So now, any questions to Dr. Chen?
Should I stop sharing? Maybe I.
Oh, no, there might be some questions to the slides. So
all right, good. Okay, go ahead.
While they are warming up, students and other colleagues are warming up, let me ask you a couple of questions. First of all, Professor Chen, thank you so much. It was a very interesting and detailed talk. But now I have a couple of questions. One is, as far as the detection concerned, you're assuming the size of the object to be relatively medium. But what about if it is medium and small? Imagine that you're crossing and you have also a pit that it is following you. I have never seen any example of this.
Okay. So for standard testing, for example, in this case, we even didn't assume we have a group of pedestrians walking through, right? So it's I cannot answer. I don't know exactly how I answer this question.
Let me just maybe add a few things in here.
Can you make it simple?
Yeah. Question really is, because detecting a small object is different than detecting relatively medium or big object.
Sure.
So it's going to take its own, like a lot of people, I'm sure Dr. Karimuddini, your team, been working on different techniques, especially nowadays, everybody is in love with deep learning. But we also have some technique for a small object that if you are interested, we can also share it with you. I think this is, to me, it is important to have this kind of scenario that pedestrian walking with a pet. Or nowadays.
I got you. Yeah, I got you. Yeah, I mean, that was not the focus of our project at that time. That's an interesting question. I tell you, there's a group, Michigan Tech, so they work on deer. Deer is shorter, you know that, right? So our average 6 years old boy is taller. So they work on deer, like an animal type of things. Then there are people working, even for baby type of size, 2 years old. They feel in cities, even look at in European cities, the streets are very narrow, very small. You have kids, younger kids, probably walking, running around. You're absolutely right. So this work focused on the US scenarios, and we did not include the small things there in terms of testing scenarios. Thank you.
And then your 110 car scenario, the data, do you think that data is available for public too?
Oh, excellent question. We have been asked a question like this for the last many years. And the good news is one of my colleagues, I don't know if you have ever met him. So he has been with us since 2010 from his PhD and all the way now. He just got an NSF Career Award anyway. So he is putting them together. We have a website. We're doing internal testing right now. And we are taking care of a lot of legal paperwork, to share data with people in academic, world. We also need to have some kind of legal protection for us. So we have things like an agreement you have to sign. We have some limitation. So we're putting some good, processed data. I call the annotation data out there, not a raw data, for people to use as some kind of benchmark so they can test their AI algorithm, for example. Good question. I will definitely keep you in mind once we make the data public. It's not all the data, we try to do face by face.
Dr. Chen, you're going to be in Lafayette on June 23rd and 24th. If you have time, please join us.
So you are coming here June
23rd and 24th, yes.
Okay, can you send me email about that?
Of course.
I should be in town by that time. I don't know some other travel schedule, but I know early June I am going to Germany,
Okay.
For the conference.
Okay.
Send me email. I think you still have my email.
Yes, I do. Yes, I do.
Yeah. By the way, I wrote her, support letter for your student, former student.
That's right. That's
for
right.
her green card application, I think.
Yes, it was. What is it?
I don't remember name.
Yeah, I know.
Okay, so
okay, good.
Yeah, maybe let's. So, any other question?
Okay, I have a question to Professor Chen. So, Professor Chen, how you make sure the robustness of your model, because as it is an integrated system, the model need to detect the pedestrian at the same time. It need to, automatic emergency braking need to stop the car within a short time. So, how you ensure this your detection system is robust enough that it can detect ahead of time, and what should be the frame per second to make the system working properly?
Okay, that's a great question. I tell you, the focus of this is research was not to develop a robust detection algorithm. I mentioned the detection because we need to process a lot of video data. We cannot just rely on our laborers, our students to watch video and identify those scenarios. So we didn't design the vehicle AEB system for commercial vehicle. So we only tested the production vehicle available, from OEM. I hope that answers your question. So those algorithms, I'm sure they are proprietary to OEM, like a Volvo, like a Toyota. So I just want to make sure we did not develop that control system, real-time control system on vehicles.
Right. Thank you. One question, Dr. Chen. Usually, what we, is one of the concern is the repeatability of the experiments and making sure that let's say the relative distance of the pedestrian and the car when you trigger the pedestrian, the dummy pedestrian to pass the crossing is going to be exactly similar to the previous cases and so on. And I was noticing that, for example, you were using joystick to trigger the pedestrians. Do you think that putting both, on the robot that is carrying the pedestrian, the platform that is carrying the pedestrian, also equipping with some sensors, so that depending on the relative distance and velocity and so many other parameters, then you can trigger the dummy pedestrian to cross the street. In that way, you can make the experiments more similar situations.
I tell you what, the videos I showed you from several years ago, and one thing I didn't mention is this suite of technology have been licensed to a startup company by Toyota and our university, and for their production system, they are more precise. So to answer your question for our experiment, we can do repeated testing very well. We didn't use other manual triggering system. We have a sensor box. On both two sides of like a road track. When vehicle pass, that line, it will trigger the whole system. So we have timing to trigger the pedestrian motion control system. So every time it's the same place. You know what I mean? It's the same place to trigger that. When you say joystick, I think it's for bicyclist testing. For bicyclist testing, for that small mobile robot, we use a joystick to control the motion because at that time we didn't have time to have that really automatic control to follow the path. The test track surface was very rough. That very low base mobile robot platform cannot travel in straight line. So we have to use a manual control. Maybe that's a joystick you talk about. Otherwise, we didn't have a joystick.
I see. Yep, that's exactly what I was asking. Thank you. So, any other question? Maybe we have two more maybe one last question before 4:10.
Sorry, I cannot hear. I cannot hear.
There is a lot of noise there. If you can type in the chat box, I can read it.
Yeah, it's noisy.
Right. No, we cannot hear.
Right. No. Yeah, read a chat, maybe.
Yeah, maybe type in chat box.
Yeah.
Okay. Any other question before typing the question in the chat box?
I can stay a few minutes longer if you like, if there are more questions.
Okay.
Okay.
Here is there is a question in chat box saying that how to extend this method to 3D pedestrian detection problem, sort of things. I think the question is that the data that you collected is primarily based on regular cameras. Do you think that this procedure can be extended to other sources of information to make it sort of useful for 3D pedestrian detection as well?
That's a good question. So 3D pedestrian detection, if they can use this data for that, I have to check with some of my colleagues, because I have a colleague in our project working on image processing, 3D video things. Right. So I will ask her if we can use our data set. So that's the question, right? If we can use this data set to test a 3D pedestrian detection algorithm.
Right. Right. And perhaps the answer might be quite challenging with this the current data set, unless it's, for example, provided by additional sources of data, let's say LiDAR data or different type of camera, or if you do have the plan to do so.
Oh, by the way, yeah, that's a good question, and also good answer from you. We are collecting, I showed a slide with a car with 6 cameras and a LiDAR. And we're collecting a lot of data, but for the last 2 years, the focus was e-scooter. But of course, when you drive around, you see people, you see bicyclists, you see pedestrians. We have those data available. But when we can make those available to researchers, that's another, topic.
I see.
So yeah, we will have those data for sure, because we have 6 cameras, we can really look at it from different angles. So in a sense, you can look at the 3D.
Exactly. Yep. Right. Yeah. Right. If that data set with the geometry of the camera locations and so on is being released at some point, I'm sure that a lot of people are going to get benefited.
Yeah. By the way, for your research group, if anyone, I don't know who asked the question, a faculty or graduate student, we can work, on this based on, individual interactions. So I'm sure we can share raw data with you if you work on 3D pedestrian detection. If we got 6 camera data, most time 2 or 3 camera, capture one object, right? So if you feel you can use, and again, we have a 360-degree LiDAR.
That's wonderful.
Data too, for the same data collection.
That's exactly what I think Redwan was asking. Yeah, that would I will follow with you and read around later.
Okay.
About that. Great. Thank you. I think it's now 4:12. So thank you so much again, Dr. Chen, and for a great talk today.